Hi, everyone. If there is a strong enough linear correlation between x and y, you might want to test to see if the alternative is holding up well, rho is not zero, then we may want to find the least squares regression line. So basically, what is the best fit line for the data, for scatter plot bivariate data? And what's the criterion? So here's the idea. Imagine that these are data points. This is Wikipedia. Imagine that these are Wikipedia on linear regression. So each of these is a data point, okay? The signed linear distance from the regression line is called a residual or an error. Here, the residual or error is negative. And the idea is that we want the line that will have the following property, that will minimize the sum of the squares of these residuals. There is one line that'll do that. It's kind of a calculus problem. There's one line that'll do that, that'll minimize the sum of the squares of these residuals. This is a line that best fits a scatter plot in the sense that the sum of squared errors or residuals is minimized. Y is the dependent or response variable, like midterm 2. X is the independent or predictor variable, like midterm 1. Now, bear in mind, sometimes the same regression line may fit very different looking data sets. This is called Anscombe's quartet. And outliers can be very influential on these things. All right. Now, remember, if we want to describe this line, we can use slope-intercept form, which is y equals mx plus b. Now, we could put the b in front and say y equals b plus mx, where m is the slope. The slope tends to be more important than b, which corresponds to the y-intercept. Now, the idea is that the true best linear regression line, least squares line, is given by this. Y equals beta naught, which corresponds to the y-intercept, b here, 0 comma b, plus beta sub 1, x. Beta naught and beta 1 are population parameters. And those can be estimated by sample statistics, b naught and b1. Y hat equals b naught plus b1x. This is the sample linear regression line, as opposed to the population linear regression line. Again, this analysis is sensitive to outliers, and the regression line may fit to a variety of different scatter plots. Now, one of the most important things about slope that you don't know is that you can interpret slope as marginal change. For example, if the house value in terms of years is given by y equals 50,000 plus 10,000 x, where x is the number of years since 2000, let's say. That means that for every year that passes, $10,000 is the increase in the house value. 10,000 here, $10,000 is the slope. So let's say that we have paired sample data for midterm scores in a class, x comma y, where x is the midterm 1 score and y is the midterm 2 score. And let's say that the least squares regression line for a sample is given by this. Y hat equals 10 plus 1.2 x. Y hat is the predicted midterm 2 score based on a midterm 1 score of x. The idea being that let's say I base this model on previous semesters, and I find out your midterm 1 score and tell you what it is. And you ask me, hey, professor, what do you think my midterm 2 score is going to be? I can use this formula. So if you got 10 points of midterm 1, I hope you didn't, but if you got 10 points of midterm 1, then I'd say that I predict a 22-point score for you on midterm 2. So according to this particular regression line, okay, for every 1-point increase in midterm 1, the x score, there is a 1.2-point increase in the midterm 2 score, the y score. So the slope here indicates marginal change, the increase in our estimate for y, our prediction for y, for every 1 unit increase in x. So for example, a student who scores 20 points on midterm 1, if you plug that in, is expected to get 34 points on midterm 2, while a student who scores 1 more point, 21 points on midterm 1, would score 1.2 more points, 35.2 points on midterm 2. For every 1 point increase in x, there's a 1.2 point increase in y, the slope. The idea of regression to the mean. In terms of standard deviations, a person should expect to score closer to the mean on midterm 2 than on midterm 1. So for example, let's say that for midterm 1 and midterm 2, on both tests, the mean is 50 points and the standard deviation is 10 points. On midterm 1, you score 70 points. You score 2 standard deviations of the mean. You should feel proud of yourself. But then on the next test, you score 60 points. And you go, oh my gosh, what went wrong? Actually, that's expected. The idea is that if a student does extremely well in midterm 1, then it is likely that errors such as luck worked in their favor. But it's also expected that the student will not be as lucky on midterm 2. So this here, that's expected. Don't be so hard on yourself. So people who don't understand this may overestimate the corrective value of punishing poor performance. So if someone goes up from here to here, right, and what happened in between was that the parent punished the child, the student, well, then that punishment might be misinterpreted. Likewise, if you're going from here to here, and you notice that you've been dealing with your iPhone a lot, you've been playing with your iPhone a lot, well, this decrease may not be due to your iPhone use, it's just regression to the mean. So don't overestimate the detriment caused by rewarding superior performance. Like if you reward yourself with an iPhone and play with it, this here can be explained by regression to the mean, not your iPhone. The Sports Illustrated Jinx is a famous example of this. The Jinx claimed that athletes who appear on the cover of the magazine one year then tend to decline in their performance the following year. Well, when does an athlete appear on the cover of Sports Illustrated? Well, typically when the athlete has a great year, right? Which means that the athlete was probably lucky that year, which also means that the lucky probably won't be as lucky next year. That's the idea. This might be related to the Oscar jinx. Finally, remember R is the linear correlation coefficient for a sample. R squared is the coefficient of determination. In percent form, it gives us the percent of the variance in y that is accounted for by x and the regression line. So for example, let's say we have the midterm 1, midterm 2 situation. In the scatter plot below, r equals 0.80. This is more typical for what I see in a calculus test at UCSD. R squared, or 0.8 squared, is 0.64, or 64%. So that means that 64% of the variance in the midterm 2 scores is accounted for by the midterm 1 score and the regression line. By the way, the regression is a bit flatter than you might think visually because of regression to the mean. All right, if r is 1, then r squared is 1, and everything's on a straight line. That's statistics, folks.